Hello and welcome to problem 18 in my Calculus 3 or multivariable calculus problem solving series. In this video, we're going to look at how to solve triple integrals using cylindrical coordinates. So in previous videos, we've used polar coordinates to solve double integrals. Where in today's video, we're going to use cylindrical coordinates to solve triple integrals. So what are cylindrical coordinates? Well, they're very similar to polar coordinates, except they're in 3D. So instead of having x, y, and z, you now have r cosine of theta, r sine of theta, and z. Where r is the distance from the x on the xy plane, theta is the angle from the x-axis, and z stays the same. Z is the height. And just like in polar coordinates, the element of volume for your triple integral is going to be r times dr d theta dz. And the reason for this is because if we take a look at one of the small pieces of volume, so this is going to be dv, the volume will be dr times r times d theta times dv. And so in our triple integral, this is what we're going to use to integrate. So let's go ahead and look at an example of how to use cylindrical coordinates to solve triple integrals. So now let's go ahead and look at an example of how to solve triple integrals in cylindrical coordinates. So this example, we have a cylinder of radius 3 and height 5, and we want to take the triple integral over this volume of the function f of x comma y comma z equals x squared plus y squared. And when we convert this into cylindrical coordinates, we know that x squared plus y squared is r squared. So this is what we're going to be integrating. So now let's go ahead and define our bounds. So the bounds for our triple integral are as follows. Theta will be from 0 to 2 pi because we have one full rotation for the cylinder. R will be from 0 to 3 because our radius is 3. And z will be from 0 to 5 because of our height being 5. So now we can define our triple integral. And it looks like this. And we have the integral from 0 to 5 for z, the integral from 0 to 2 pi for theta, the integral from 0 to 3 for r, of r cubed. And the reason we have r cubed instead of r squared like before was because of that extra r for dv, the small piece of volume, and it has the extra r, so r squared times r is r cubed. So now we go and solve this like any other integral or any other triple integral. So the integral of r cubed is r to the power 4 over 4 from 0 to 3. And that's going to equal 81 over 4. And when we take the integral for theta, so the integral of 81 over 4 with respect to theta is 81 over 4 times theta. And theta goes from 0 to 2 pi. So it's going to be 81 over 4 times 2 pi, or just 81 pi over 2. Then we have the integral from 0 to 5 for z. So it's just going to be 81 pi over 2 times z. And z goes from 0 to 5. So it's 81 pi times 5 over 2. Or 405 pi over 2. Which is approximately 636. And this will be our final answer. And remember that this can also represent the mass over the volume of our cylinder. So an alternate way to solve this problem is to get the average value of the function inside this circle and multiply it with the volume of the cylinder. Because getting the average value of the function and multiplying with the volume will give you the mass. So we can rewrite a new function, f of x comma y, which is equal to x squared plus y squared, like our old one. And the volume of this cylinder will be pi r squared times h, or pi times 3 squared times 5, because we have a radius of 3 and a height of 5. And what we're going to do is to find the average value of the function. So with the average value, we can find what we're looking for. So to find the average value of the function, so this is the xy plane, x and y, we can rewrite the function in terms of r. So f of r is r squared. And we're going to take a slice of this circle. So we have a very small change, or dr, and we want to find the area of this small piece. So the circumference, or the length, will be 2 pi r, and this side will be dr. So our small piece of area, dA, is 2 pi r dr. So the average value of the function times pi 3 squared, or the area of this circle, is equal to the integral from 0 to 3 of f of r dA, or the integral from 0 to 3 of r squared times 2 pi r dr. So this is dA, and this is f of r. And so now, when we solve the integral, we can find the average value of the function. So we get 2 pi r to the 4th over 4 from 0 to 3. And we get that the average value of the function times pi times 3 squared equals 2 pi times 3 to the power of 4 over 4. And we can simplify, so we cancel out 3 squared on both sides, and we cancel out pi, and we find that the average value of the function is 9 over 2. So what this means is, to find what we're looking for before, we have to multiply this value by the volume, or pi times 3 squared times 5, and we get 636, about, which is the same as we got before. So that's going to be it for this video. Thanks for watching.